Hi everyone. Today in the Explore section of your landslide investigation, I'm going to show you how to use the slope stability worksheet. So we're going to go through the worksheet A together for the Westchester County, New York landslide back in 2023 that you've read about and explored already in this investigation. So the location name specifically in Westchester County is Briarcliff Manor. So I'm going to write in Briarcliff Manor and we can underline that. And the coordinates of that location with our latitude and longitude. To analyze these slopes, we have to look at some of the information provided in Google Earth. We'll have to take some measurements of the slope height, the slope length, depth to water table, and some of the soil profile conditions, which we'll find in the New York State well reports from the Department of Environmental Conservation. So the first thing we'll take a look at is we'll make some measurements of the slope here in Briarcliff Manor in Westchester County. So to do that, we're going to go to Google Earth, and these little icons here show us all the landslides that we're going to potentially investigate in this project. But for right now, we're going to go to the bottom of slope 1 in Westchester County. There's a couple of ways to do that. I'm going to show you one. If you expand this side panel and you see bottom of slope 1, if you click on the three dots, you can actually fly to that location. So this brings us to the bottom of slope 1 here in Westchester County. Now notice when I put it in this three-dimension view, you get a pretty good idea of the steepness of this slope. The water body we see here is the Hudson River, and it's very close to New York City. So this is essentially sea level right at the Hudson River. And then we have 4 sets of railroad tracks, and then the steep slope directly above, going all the way up to this retaining wall. And that's what we're going to be measuring, the height of that slope as well as the length. And this is the area that failed during that landslide that you read about earlier on in this investigation. Now, to make our measurements, it's probably best if we go back to the two-dimensional view. So I'm going to click two dimensions. And I'm also going to reset my screen orientation so that the compass is facing north. So I click on the compass icon here on the bottom, and I'm going to select reset to north. Now, for our measurements, it's important that you zoom in so we can have the most accurate measurements possible. So I'm going to zoom in quite a bit here to focus on this slope. The first thing that I'm going to record is the height of the slope. Now, to do that, it's a little tricky, but if you look down, way down in the bottom right corner here, you see the 4 meters. That's 4 meters of elevation based off of where the cursor is. So I'm going to move the cursor, and as I move that, here I'm at the bottom of the slope now. Notice that it's very close to zero. I'm just a few centimeters above sea level. So essentially we'll call the bottom of the slope 0 meters right at sea level. Now if I move the cursor up to right inside the retaining wall, right about here, you'll notice down at the bottom it's indicating 15 meters. So the height of our slope is roughly 15 meters. Let's record that. Now 15 meters, remember we're using the metric system here, is pretty high. So 15 meters is roughly a 4-story building or so. Our rough estimate is you take your 15 and multiply it by 3 to get the feet. So we're looking at about 45 feet of height here, roughly a 4-story building. Next, we need to measure the length of the slope, again in meters. So I go back to Google Earth, and we have a tool for that. If you look up at the top of our Google Earth, you'll see this little ruler icon. And we're going to click on that to measure the distance. So we're going to measure the distance from the bottom of the slope. Get your pointer right at the little icon. And we're going to measure all the way up to the top of the slope, right inside the retaining wall. And if I'm right inside there, I'm right around 20 meters. So 20 meters for the height of our slope. So let's record that. 20 meters, I should say, for the length of our slope. Now, the next thing we need to figure out is the average depth of the water table in meters. And that's where we're going to use our New York State DEC well report. So I'm going to click on that, and it'll bring up this report, which is a little confusing. There's a lot of information here, and we don't need all of it, but we will need a few things. And the first thing we need is depth to the groundwater. So depth of the groundwater is right in this region, and it's 40 with a unit of feet. So 40 feet below the land surface is our water table, or the depth to groundwater. So looking at this in a picture view, we have the top of the well, and as they drilled down through, they drilled through some fill dirt, some loose sand soil. They eventually hit bedrock at 32 feet, and then just below that would be the water table. And you notice they continue to keep drilling deep into the water table, as the purpose of these wells are to generate certain gallons per minute. So for our purposes, again, we just need depth to groundwater at 40 feet. So let's record that. Now, 40 feet, before I continue, we're going to have to convert that into meters. So instead of 40 feet, we're going to roughly divide that by 3, and that'll give us a rough estimate of about 12 meters down into the soil before we reach the water table, groundwater. Now, the soil profile, again, this comes from the New York State well report. We talked about fill dirt, which was placed by builders, kind of making ground, loose sand soil, and then eventually reaching bedrock. This is a little tricky to figure out. So we've provided some of this information for you. If you go back to Google Earth and you click on the little icon for the bottom of the slope, move that out of the way, you'll notice we've given you some of that information, and we'll record that so we can use that information in our calculator that'll help us figure out the stability of the slope. Also, notice at the bottom of slope 1, any of these icons give you a little idea on where to make your measurements, as we did. We measured from the point where the lawn starts at the retaining wall. So I'm going to record this information about the soil profile in our lab report. So let's go back to our lab report, and we're going to have our soil profile of 4 meters of fill, which is placed there by humans. We call that made ground. After that, working down, we have 6 meters of loose, poorly sorted sand. And then below that, we're going to use a 7 meters of what we call a custom layer as we enter the bedrock. So that's the information we'll need in our calculator. So speaking of our calculator, we're going to go to our calculator, and we're going to take this information of the slope height, length, depth of water table, and our soil profile to determine the stability of the slope. So I'm going to open up our slope stability calculator, and I'm going to change some of those properties that we recorded. So the slope height, we need to change this to our slope height of 15 meters, a slope length of 20 meters, and the water depth in this particular case was 12 meters. Now, before we can run the analysis, we need to change some of that soil profile. And to do that, we go to the Edit Geology section. So Edit Geology, we'll click on that, and we're going to change some of the soil profiles for our particular location. So that made ground, we had a thickness of 4 meters. Our next layer below the made ground in our particular case was the loose, poorly graded sand. So I'm going to open this up. There's a lot of choices here, so I'll have to read down quite a bit. But here's our loose, poorly graded sand. And that had a thickness of 6 meters, we estimated, for that layer. And we're going to add a new layer here. It's going to be that custom layer as we approach the bedrock, and we're going to say we had about 7 meters in that layer, and we can click Save Changes. At this point, we can analyze our slope by hitting Analyze here. And you're going to notice we're really close to 1.0. So 1.0 is kind of our our cutoff point for slope stability. So our slope is at the moment stable, but has the potential with any slight changes in groundwater or any changes in the length of the slope, if it's undercut, to become unstable at any moment. So with that, we can go back to our report and we can say it's currently stable with a factor of 1.03. And again, that's really close to the unstable level. Once you get below 1.0, the slope is considered unstable. And that's actually what you're going to work on here when we bring in some other variables like extreme weather events where we may have days and days of heavy rain and the water table changes. Or if we have human activity, like I mentioned, we decrease that length of the slope, it'll have an impact on how that slope stability is calculated using the calculator. So hopefully this is helpful. If you have any questions, reach out to your instructor and we're here to help you.